Let me explain this problem. You have an array of integers, and for each operation, you need to choose an integer x, and you turn integer ai into the lower Gaussian's function of ai plus x over 2. So here is the operation, and you do this operation for all I between 1 and n. So how many operations do you need um, at minimum to achieve a situation such that all the integers are the same? So that is the problem. And our first hint is that you only need to consider the maximum and the minimum values because this function is actually um, this function is actually an increasing function. So if you look at f of x, which equals to the Gaussian function of a of I plus x divided by 2, when x increases, this fx will increases. So suppose initially there are x1 smaller than x2 and all the way to xn, they are in an ascending order. Then no matter how many times we apply the function f to the array x, they will still be in ascending order. And we know that um, at the end of the operations, they are the same. The fact is that we only need to guarantee that f of x1 is equals to f of xn. If this condition is true, then f of x1, x2, and all the way to xn will all be the same. This by f, I actually mean that we apply f to array x for m times. So this is the task that we want to solve. To solve this task, here is our second hint, which is that we consider the maximum value minus the minimum value, which is xn minus x1. And we observe this value. How will this value change after an operation? So we can divide it into some cases. First case is that x1 and xn are um, they are equivalent when modular 2, which means that they are both odd or both even. If they are both odd, then we will pick x as 1. So if we pick x as 1, then xi plus 1 over 2. Xi will change to this, and xn will change to xn plus 1 over 2. And then the difference between these two numbers after we do an operation is 2 um, is a half of xn minus xi, whereas the distance between these two numbers, which are the numbers before the operation, is xn minus xi. So we can see that after an operation, the distance is divided by 2. This can be also be true for xi and xn are even. We can pick x as 0. So another case is that xi and xn, they are not the same. They don't have the same in term of odd or even. So let's say xi is odd, whereas xn is even. So in this case, no, x1 is odd, xin is even. So previously when I say xi, I actually wanted to mean x1. In this case, we want to pick k equals to x equals to 1. So after we do an operation f, you can see f of xi is equals to xi plus 1 over 2, whereas f of xn is equals to xn over 2. So before the operation, the difference between xn and x1, yeah, I actually wanted to mean x1 here. So before operation, the distance between xn and x1 is xn minus x1, whereas after the operation, the distance between them is xn minus x1 minus 1 over 2. So we can actually see that regardless of um, x1 and xn are even or odd, the distance between them after we apply an operation will divide it by half. And if it divided by half is not an integer, it will divide it by half and then round to the biggest integer that is less than or equal to it. So xn minus x1 will be changed to the xn minus x1 divided by 2 and Gaussian function here. We can have a proof that no matter how we choose x, this will go to, so xn minus x1, their difference will be divided by half in the best case. So we can't make the difference smaller. You can prove that by by considering the odd or even x, because x is what number is not important. The important thing is that x is odd or even. So by doing some casework, you could show that the best x values we can choose will result in the difference being divided by half. Therefore, here comes the answer. The answer is the number. So we want to make it 0. Therefore, the answer would be k, smallest k, such that 2 to the kth power is greater than um, xn minus x1. So this k will be our answer to this question. Therefore, the time complexity will be O of log um, L, which is L is xn um, minus x1. So the problem is over, and thank you for listening.